Hello, my name is Michael Stengel and I'm a research scientist with NVIDIA. I will talk about our work on a system for streaming light probe data for decoupled rendering in server-client architectures. The current generation of cloud gaming streams full frames from the server to the client. This allows the client to be very low power but introduces latency and saturates the available network bandwidth already for a single high-quality display client. Fast-paced games such as Fortnite require less than 100 milliseconds click-to-photon latency to play competitively. Remotely rendered content can suffer from higher latencies due to network congestion. Things are even more challenging for VR and AR. Soon we will see the need to support 4K resolution per eye and refresh rates of 120 Hz or higher. This increases the required bandwidth for remote rendering. Another challenge is interaction latency. A game like Half-Life Alyx requires precise hand interaction and quick reaction. It is very difficult to predict this kind of interaction. All these factors are challenging for the final content being rendered in the data center. Computing indirect lighting, also called global illumination, in real time is computationally expensive. This is especially challenging for thin client devices, such as VR headsets or mobile gaming consoles. However, human vision is less sensitive to delayed indirect lighting than it is to delayed primary visibility. This motivated us to stream dynamic probe volume data from a cloud server to the client instead of being ray traced locally. Only direct lighting is being computed on the device. In combination, the achieved quality on the device is high without introducing network-induced user input latency. If we look at the situation in terms of application and device complexity, current solutions for gaming are typically either full 3D clients or thin video clients. For remote rendering, the program mostly runs on the server. The client can be low power as it is only buffering incoming frames and warping them to high transmission and user input latency. The transported data from server to client at high bandwidth is close to the display resolution and frame rate of the client. In the opposite direction, the client streams user input data with low bandwidth. Now, the idea of decoupled rendering is to distribute the render pipeline in a way that the client does a part of the rendering that is cheap but visually important to have low latency. The server is computing another part of the rendering that is expensive and visually acceptable to have a bit higher latency. Instead of streaming ready-to-use frames, we stream compressed lighting data, which is useful to the client to get expensive lighting effects from the server. In this scenario, the game logic is running on both ends. Another advantage of such system is that the server can reuse the computed information for many clients. Besides full frame transfer, there is only limited research in splitting the render pipeline between server and client. One of the influential papers is the Cloud Light system from NVIDIA. This work by Krasner et al. Has shown that updating diffuse indirect lighting is visually acceptable up to a delay of several hundred milliseconds. The cloud baking paper by Liu et al. Transfers a compressed GI map from the client's perspective and uses warping to match the actual client view. The regular grid GI paper by Margo et al. Uses a voxelized version of the scene. Each voxel holds GI irradiance data and is updated over time. The transferred data is compressed on the CPU. All these approaches have in common that no visibility is available on the client side. But why is that a problem? Methods using irradiance probes can provide excellent quality, but probes leak light and shadow when geometry exists between sampling position and probe position. This is due to the lack of visibility information. The traditional way to avoid the problem is manually tweaking the probe locations by artists, which is a time-consuming and difficult process and has to be redone each time the scene geometry changes. Dynamic objects are therefore completely unsupported with traditional irradiance probe methods. In this work, we focus on dynamic diffuse global illumination, in short DDGI, by Majercik et al. The DDGI algorithm is based on irradiance volumes by Greg et al. Irradiance volume methods have been around since 1998 and are supported by most game engines today. In a nutshell, you fill the 3D world with small probes that measure and store diffuse GI. Typically, the lighting stored in these probes is pre-computed offline and then sampled at runtime. The workflow of DDGI is as follows. First, during scene creation, a volume of probes is placed in the 3D world. No baking of information, UV generation, or tedious probe adjustment are required. At runtime, for the available frame budget, a certain number of rays are cast and shaded for each active probe. During the probe update step, the results are blended with previous samples to reach infinite bounds GI. The results are saved as a probe atlas storing probe irradiance and visibility as distance to scene geometry. Please note that the tracing and probe update can happen independently from screen resolution and frame rate. Finally, the indirect lighting is efficiently computed from the probe atlas data without leaks. This is a screenshot of the attic scene rendered in the Unreal Engine using the RTX-GI plugin implementing DDGI. The left half of the image includes indirect lighting from RTX-GI, whereas the right half only has the direct lighting and ambient lighting. You can see how much richer the scene looks when the indirect lighting is computed. The question is how the dynamic light probe data can be efficiently transferred to the client. On the left, we see how the light probe data is arranged in textures on the GPU. Streaming these textures uncompressed would require half a gigabit per second. We need to compress the textures significantly. This table shows different directions to compress the GI data structure. General data compression such as deflate is lossless and allows fast decompression when performed on the GPU. However, the size reduction is not enough in our case. Traditional block texture compression methods can reduce the texture size further, but will add delay for higher compression rates and also don't support depth. Super compression algorithms such as basis and JPEG allow high compression rates, but can be very slow in the case of basis and might get expensive on the decoding side for JPEG. There's also no good solution for lossless depth encoding. RVL is one of the best depth encoding techniques and is still limited to a size reduction of 3x. So in summary, only JPEG might be a path towards practical compression rates if we would accept loss. Depth compression has no good solution for higher compression rates. We can also observe that the solutions compress individual textures, so temporal redundancy in the data is not considered. So what about video compression? We have dedicated power-efficient video decoders on mobile devices and HDR support is already growing. In addition, GPUs have lossless video compression modes for encoding in hardware. And at least for videos, we see comparable or better compression performance than super compression texture algorithms. Specifically, we looked at HEVC lossless with 10-bit and 8-bit, since compression rates are higher than with H.264, and mobile devices slowly have support for that format. So how do we perform irradiance volume compression with a video compressor? We want to encode our data visually losslessly for high-quality GI. To use the video encoder, we must convert the texture data into YOV color planes. For irradiance, we use HDR compression at 10 bits per color. For encoding, the data is stored in 16-bit color planes, but the encoder uses 10 bits. For visibility, we distribute one depth value across two LDR color channels. 4 YOV pairs are required to hold 3 visibility pairs. This results in a texture that is enlarged in the first dimension. This hurts compression performance, but we will see later that the compression is still better than other floating point compression strategies. One obvious size reduction we also apply before encoding is removal of the texture filtering guard band around each probe core in the DDGI atlas. The guard band can be reconstructed from the probe cores after decoding, so there is no loss in information. This reduction steps saves 36 and 21% for irradiance texture and visibility texture in raw texture size. Our probe volume encoding can achieve high compression performance. The actual ratio strongly depends on the success of the encoder prediction. The compression performance is significantly better than single frame and fixed ratio compression schemes. Another observation is that we achieve slightly higher compression performance with larger probe grids and higher frame rates. This can be explained with a smaller frame-to-frame change of the underlying texture data. We also see that the visibility data requires more throughput since floating point compression performance is overall lower. In the following, I will present the architecture of our research prototype that distributes the global illumination graphics pipeline across server and one or more clients, instead of streaming full video frames. The server in the data center conceptually consists of a game server and the global illumination or GI server. As it is typical for online gaming, the game logic runs on the client and on the game server. We use a multi-threaded RUDP implementation that allows unreliable and reliable connections with low latency. This enabled to max out the available bandwidth with loss rates up to 4%. In practice, we don't expect higher loss rates, and at least for texture transfer, consider higher throughput more important than reliable transfer. A reliable connection is used to exchange user input data and game state updates between server and client. In addition to the game server, we add a second cloud-based node, the GI server. This node has access to the scene state from the game server and regularly updates GI data using DDGI. For each client, light probe data is optimized and encoded using hardware-accelerated, high-efficiency video compression. Note that this compression is lossless and includes irradiance and visibility data in separate textures. The GI texture data is updated selectively at varying rates as an optimization to reduce the texture size. The compressed GI data is reliably transferred to the client. On the client, the decompressed GI probe textures are used to efficiently include fully dynamic decoupled GI in the render loop. Decompression of the data uses the hardware video decoder. This allows the render loop to run at full frame rate, avoiding additional input-to-output latency. We realized the system prototype with a research game engine. You can see here 3 scenes with different levels of dynamic lighting and dynamic geometry. In all of these scenes, diffuse global illumination contributes significantly to the look of the final rendering. This video shows a scene with fully dynamic lighting from a simulated day-night cycle. You see the primary visibility and direct lighting rendered on the client. The diffuse indirect lighting is efficiently computed at low cost using the streamed light probe atlas. In combination, we achieve to render high-quality, fully dynamic scenes at display frame rate. In the chart on the right, you can see the amount of data transferred across the network for probe streaming. The light probe textures are updated at a limited rate adjustable to the network bandwidth conditions. Overall, we achieve significant bandwidth savings due to our lossless compression scheme compared to the original uncompressed data. We experience higher consumed bandwidth when the lighting conditions change quickly. In these cases, the frame-to-frame difference in the light probe color atlas are larger, increasing also the size of the encoded data. We also tested the approach in VR. The user can control the virtual flashlight with a hand controller. The game server is informed about the controller position and allows the GI node to generate the lighting data accordingly, which is then streamed back to the client. We use CloudXR to stream the final frames from the client computer to the Oculus Quest VR headset. Motivated by our results so far, we ask ourselves what else we can do to reduce the size of data transfer. We only want to transfer data that actually contributes to the client view. So we came up with the idea of a selective probe update. For a probe to be selected for transfer, it needs to be active, meaning to hold information about surfaces, visible to the user, and the probe values need to have changed from frame to frame. We therefore cull probes that don't contribute. Here, we visualize the client probe culling approach. Top left is the client reference view that the server is aware of. The server now estimates for the known view which probes are used for rendering the client view by tracing a low number of arrays. The most aggressive probe culling result is shown in the top right. Since the server receives the client view info with some latency, it can happen that the client looks at part of the scene with outdated GI information. We show here the worst case scenario, where no GI data exists in the culled parts of the GI volume. In practice, the image wouldn't be black, but would only contain outdated GI data. In the bottom right picture, we instead render the client view with a larger margin. This way, more probes are selected so that the client can safely move his camera view. This view looks equivalent to the case where all changed probes have been selected, but needs a significantly lower number of probes. Here we see some numbers comparing the different probe reduction techniques. The number of probes is roughly reduced by 66% by an aggressive probe culling and by 50% by estimating the potentially visible probes. With increasing probe volume, these methods also get more effective since the selections can be made more accurately. This diagram shows the described architecture including probe selection and client probe culling. Please note that the probe index buffer can be compressed well, so we don't add much overhead by selective probe streaming. Click-to-fault and latency is a critical metric in cloud gaming. Note that in this table, we break down the latency for the full distributed system for indirect lighting. We compare 2 different clients. Client A is using a 2080 Ti desktop GPU. Client B is a low-power mobile client using Xavier X. We also include values here for lossy irradiance encoding, which is significantly lower. The combined latency is between 20 and 35 milliseconds, excluding network transfer latency and user input latency. If we assume 150 milliseconds as an upper bound for combined network and input latency, we are still under the latency limit recommended by the CloudLight paper. Here you can see time plots for different settings for client A, connected to the server via internet over 3 hops. The left plot shows the latency for lossless encoding and without any of the advanced probe reduction schemes. The second plot shows improved latencies when we switch to high quality but lossy irradiance encoding. From time to time we see spikes in the latency whenever we transfer a reference frame, but with reliable transfer we actually don't need regular reference frames. With a longer group of pictures encoding, we can avoid most of the delayed frames and achieve an average latency of 53 and 45 milliseconds. If we activate probe culling, we further reduce texture transfer latency to 37 and 39 milliseconds. On the right, we see in comparison the plot for local transfer of losslessly encoded textures. The time series plots for file transfer size show an equivalent picture. We see an increase in texture size whenever the lighting or visibility changes more drastically. In the worst cases, for losslessly encoded iframes, we have to transfer textures of 1 megabyte in size, which takes quite some time. Deactivating iframes reduces the worst case frames to 150 kilobytes in size. When activating selective probe update, we achieve an average transfer size of 10.5 kilobytes for irradiance and 0.7 kilobytes for visibility, although the lighting in the scene is very dynamic. Again, on the right you see the comparison plot for local transfer. To sum up, our decoupled distributed light probe streaming system enables indirect lighting on low-end devices without input lag for primary visibility. We use hardware-accelerated video encoding and show that the encoder can exploit temporal redundancy in the lighting data. The distributed rendering paradigm allows new GPU features to be deployed much earlier as part of the rendering happens in the cloud. And last but not least, our approach opens the path towards amortizing render costs across clients and shared experiences. I want to thank at this point all the contributors on the project. With this, I want to thank you for your time.